In group theory, the direct product is an operation that takes two groups G and H and constructs a new group, usually denoted G times H. This operation is the group-theoretic analogue of the Cartesian product of sets and is one of several important notions of direct product in mathematics. In the context of abelian groups, the direct product is sometimes referred to as the direct sum, and is denoted GH. Direct sums play an important role in the classification of abelian groups. According to the fundamental theorem of finite abelian groups, every finite abelian group can be expressed as the direct sum of cyclic groups. Definition: given groups G and H, the direct products G times H is defined as follows. The elements of G times H are ordered pairs, where G, G and H, H. That is, the set of elements of G times H is the Cartesian product of the sets G and H. The binary operation on G times H is defined component-wise, equals. The resulting algebraic object satisfies the axioms for a group. Specifically, associativity. The binary operation on G times H is indeed associative. Identity. The direct product has an identity element, namely, where 1G is the identity element of G and 1H is the identity element of H. Inverse is the inverse of an element of G times H is the pair, where G-1 is the inverse of G in G, and H-1 is the inverse of H in H. Examples: let R be the group of real numbers under addition. Then the direct product R times R is the group of all two-component vectors under the operation of vector addition. Plus equals. Let G and H be cyclic groups with two elements each. Then the direct product G times H is isomorphic to the Klein-4 group. Elementary properties. The order of a direct product G times H is the product of the orders of G and H. G times H equals G H. This follows from the formula for the cardinality of the Cartesian product of sets. The order of each element is the least common multiple of the orders of G and H, equals LCM. In particular, if G and H are relatively prime, then the order of is the product of the orders of G and H. As a consequence, if G and H are cyclic groups whose orders are relatively prime, then G times H is cyclic as well. That is, if M and N are relatively prime, then times Z, M and Z. This fact is closely related to the Chinese remainder theorem. Algebraic structure. Let G and H be groups. Let P equals G times H, and consider the following two subsets of P. G equals GG and H equals HH. Both of these are in fact subgroups of P, the first being isomorphic to G, and the second being isomorphic to H. If we identify these with G and H, respectively, then we can think of the direct product P as containing the original groups G and H as subgroups. These subgroups of P have the following three important properties. The intersection GH is trivial. Every element of P can be expressed as the product of an element of G and an element of H. Every element of G commutes with every element of H. Together, these three properties completely determine the algebraic structure of the direct product P. That is, if P is any group having subgroups G and H that satisfy the properties above, then P is necessarily isomorphic to the direct product of G and H. In this situation, P is sometimes referred to as the internal direct products of its subgroups G and H. In some contexts, the third property above is replaced by the following. 3. Both G and H are normal in P. This property is equivalent to property 3, since the elements of two normal subgroups with trivial intersection necessarily commute, a fact which can be deduced by considering the commutator G H of any G and G H in H. Examples: let V be the Klein-4 group. Then V is the internal direct products of the two element subgroups 1A and 1B. Let A be a cyclic group of order Minnesota, where M and N are relatively prime. Then N and M are cyclic subgroups of orders M and N, respectively, and A is the internal direct products of these subgroups. Let C times be the group of non-zero complex numbers under multiplication. If n is odd, then the general linear group GL is the internal direct products of the special linear group SL and the subgroup consisting of all scalar matrices. Similarly, when n is odd, the orthogonal group O is the internal direct products of the special orthogonal groups O and the two-element subgroup -I, where I denotes the identity matrix. The symmetry group of a cube is the internal direct product of the subgroup of rotations and the two-element group -I, where I is the identity element and -I is the point reflection through the center of the cube. A similar fact holds true for the symmetry group of an icosahedron. Let n be odd, and let D4n be the dihedral group of order 4n. D4n equals R, S, R2n equals S2 equals 1, C near equals R minus 1 S. Then D4n is the internal direct products of the subgroup R2, S and the two-element subgroup 1, Rn. Presentations. The algebraic structure of G times H can be used to give a presentation for the direct products in terms of the presentations of G and H. Specifically, suppose that G equals SG, RG and H equals SH, RH, where SG and SH are generating sets and RG and RH are defining relations. Then G times H equals SG/SH, RG/RH/RP, where RP is a set of relations specifying that each element of SG commutes with each element of SH. For example, suppose that G equals A, A3 equals 1 and H equals B, B5 equals 1. Then G times H equals A, B, A3 equals 1, B5 equals 1, AB equals bar. Normal structure as mentioned above, the subgroups G and H are normal in G times H. Specifically, define functions pi G, G times HG and pi H. G times HH by pi G equals G and pi H equals H. Then pi G and pi H are homomorphisms, known as projection homomorphisms, whose kernels are H and G, respectively. It follows that G times H is an extension of G by H. In the case where G times H is a finite group, it follows that the composition factors of G times H are precisely the union of the composition factors of G and the composition factors of H. Further properties. Universal property. The direct products G times H can be characterized by the following universal property. Let pi G, G times HG and pi H, G times HH be the projection homomorphisms. Then for any group P and any homomorphisms FG, PG and FH, PH, there exists a unique homomorphism F. PG times H make in the following diagram commute. Specifically, the homomorphism F is given by the formula F equals FH. This is a special case of the universal property for products in category theory. Subgroups. If A is a subgroup of G and B is a subgroup of H, then the direct products A times B is a subgroup of G times H. For example, the isomorphic copy of G and G times H is the products G times 1, where 1 is the trivial subgroup of H. If A and B are normal, then A times B is a normal subgroup of G times H. Moreover, the quotient is isomorphic to the direct product of the quotients G, A and H, B, times. Note that it is not true in general that every subgroup of G times H is the product of a subgroup of G with a subgroup of H. For example, if G is any group, then the product G times G has a diagonal subgroup delta equals GG, which is not the direct products of two subgroups of G. Other subgroups include fiber products of G and H. The subgroups of direct products are described by Gaussat's lemma. Conjugacy and centralizers two elements and a conjugate in G times H if and only if G1 and G2 are conjugate in G and H1 and H2 are conjugate in H. It follows that each conjugacy class in G times H is simply the Cartesian product of a conjugacy class in G and a conjugacy class in H. Along the same lines, if G times H, the centralizer of is simply the products of the centralizers of G and H. Cg times H equals Cg times Ch. Similarly, the center of G times H is the product of the centers of G and Z equals Z times Z. Normalizers behave in a more complex manner, since not all subgroups of direct products themselves decompose as direct products. Automorphisms and endomorphisms. If alpha is an automorphism of G and beta is an automorphism of H, then the product function alpha times beta, G times H defined by equals beta, is an automorphism of G times H. It follows that AUT has a subgroup isomorphic to the direct products AUT times AUT. It is not true in general that every automorphism of G times H has the above form. Times AUT is often a proper subgroup of AUT. For example, if G is any group, then there exists an automorphism sigma of G times G that switches the two factors, i.e., sigma equals. For another example, the automorphism group of Z times Z is GL, the group of all 2 times 2 matrices with integer entries and determinant plus or minus 1. This automorphism group is infinite, but only finitely many of the automorphisms have the form given above. In general, every endomorphism of G times H can be written as a 2 times 2 matrix where alpha is an endomorphism of G, delta is an endomorphism of H, and beta, Hg and gamma, Gh are homomorphisms. Such a matrix must have the property that every element in the image of alpha commutes with every element in the image of beta, and every element in the image of gamma commutes with every element in the image of delta. When G and H are indecomposable, centerless groups, then the automorphism group is relatively straightforward, being AUT times AUT if G and H are not isomorphic, and AUTWR2 if GHWR denotes the Reith product. This is part of the Krull-Schmidt theorem, and holds more generally for finite direct products. Generalizations. Finite direct products. It is possible to take the direct product of more than 2 groups at once. Given a finite sequence G1, Gn of groups, the direct product is defined as follows. The elements are G1 times Gn are tuples, where G for each I. The operation on G1 times Gn is defined component-wise, equals. This has many of the same properties as the direct products of 2 groups, and can be characterized algebraically in a similar way. Infinite direct products. It is also possible to take the direct products of an infinite number of groups. For an infinite sequence G1, G2, of groups, this can be defined just like the finite direct products of above, with elements of the infinite direct product being infinite tuples. More generally, given an indexed family Gi of groups, the direct product Ig is defined as follows. The elements of Ig are the elements of the infinite Cartesian product of the sets Gi, i.e., functions f, Ig with the property that Fg for each I. The product of 2 elements f, G is defined component-wise, equals Fg. Unlike a finite direct product, the infinite direct product Ig is not generated by the elements of the isomorphic subgroups Gi. Instead, these subgroups generate a subgroup of the direct products known as the infinite direct sum, which consists of all elements that have only finitely many non-identity components. Other products, semi-direct products. Recall that a group P with subgroups G and H is isomorphic to the direct product of G and H as long as it satisfies the following 3 conditions. The intersection GH is trivial. Every element of P can be expressed as the product of an element of G and an element of H. both G and H are normal in P. A semi-direct product of G and H is obtained by relaxing the third condition, so that only one of the two subgroups G, H is required to be normal. The resulting product still consists of ordered pairs, but with a slightly more complicated rule for multiplication. It is also possible to relax the third condition entirely, requiring neither of the two subgroups to be normal. In this case, the group P is referred to as acute P product of G and H. Free products. The free product of G and H, usually denoted GH, is similar to the direct product, except that the subgroups G and H of GH are not required to commute. That is, if G equals SG, RG and H equals SH, RH, are presentations for G and H, then GH equals SG, SH, RG, RH. Unlike the direct product, elements of the free product cannot be represented by ordered pairs. In fact, the free product of any two non-trivial groups is infinite. The free product is actually the coproduct in the category of groups. Subdirect products if G and H are groups. A subdirect product of G and H is any subgroup of G times H which maps surjectively onto G and H under the projection homomorphisms. By Gaussat's lemma, every subdirect product is a fiber product. Fiber products let G, H, and Q be groups, and let phi, GQ and chi, HQ be homomorphisms. The fiber product of G and H over Q, also known as a pullback, is the following subgroup of G times H. G times QH equals G times H. Phi equals chi. If phi, GQ and chi, HQ are apomorphism, then this is a subdirect product.